Okay, so just as we did here, again, take the interval 0 to 12, divide it into n equal subintervals. And we're going to let x sub I star stand for some x within the ith subinterval. Now there are there are n subintervals, so I is some number between 1 and n, right? Okay? And if we have 1,000 subintervals, then I would be some number between 0 and 1,000. If the intervals are equal, we could calculate the left and right endpoint of the ith subinterval, right? We didn't do that symbolically. We're not going to. It'd be easy to do, okay? The point is, we just want to talk about the typical subinterval. Once we have an expression for what goes on in the typical subinterval, which we almost do, then we can just do a sum, a limit, and we get an integral. It's very straightforward. There are a lot of technicalities that we're glossing over, but we do that in an applied calculus course. In a theoretical calculus course, we obsess over those details and make sure everything is done with complete rigor. But here, we don't need to do that. Okay? We want something you can use. If you want the deeper theory, you're in good shape to go study it. Take a course where you get it. And you're plenty smart enough to do that, but you probably don't need it, so you're probably not going to do that. Okay? And that's okay. Okay, well, anyhow, here you have it. Some x within the I subinterval. Then, well, width of the subinterval is delta x, right? And delta x is something we can easily calculate. What would delta x be? Divide the interval from 0 to 12 into n equal subintervals. How wide is each one going to be? If they're all equal, there are n of them. Total width of the intervals is 12, right? So you just divide 12 by how many there are, and that's how wide each one has to be. So that's obvious, you just didn't want to say it. Okay? So that's the width of your subinterval. I'm just going to call it delta x, but we know we can calculate it. Well then, corresponding contribution to the volume of the solid of revolution is what?